May I now request Director Professor Gautam Biswas to welcome Professor Talukdar with a gamucha. Thank you, sir. I would now like to invite Professor Mohanta, Dean of Faculty Affairs, to deliver the welcome address.
Director IITGuwahati, distinguished invited guests, colleagues and students, a very good evening to all of you. As all of you are aware of, that 5th September is observed as the Teachers' Day throughout India to commemorate the birth anniversary of great scholar and teacher and former President of India, Dr. Sarvepalli Radhakrishnan. This type of Teachers' Day is actually observed in the world in different dates. World UNESCO has fixed the date of 5th October. For USA it is 5th October. For China it is 10th of September. It is like that. But in case of India, it is due to commemorate the birth of Sarvepalli Radhakrishnan. It is fixed as 5th of September. And it has been continued till the year 1962. Previously, in last 2 years, we conducted such program from the Faculty Affairs Office. Today, we thought to make it in a bigger fashion, but maybe because of certain constraints, many of the faculty and students could not join us. Maybe later on they will join us. Anyway, in this particular program, we invited 2 distinguished guests, and they accepted our invitation. One is Dr. N.C. Talukdar, who happened to be the Director of Institute of Advanced Studies in Science and Technology, Guwahati. The second lecture, which will be started after the tea break at 6:30, is named as Institute Lecture. It will be delivered by Padma Bhushan Professor M.S. Raghunathan, FRS. I take the privilege here to welcome all of you to this auspicious event, and my heartiest regards and respect and best wishes to all my teachers and teaching community. Hope it will be a memorable evening for all of you. With this, I'd like to thank you.
Thank you, Professor Mohanta. May I now request Professor Gautam Biswas to please come and deliver the opening remarks. Thank you.
Respected guest, Dr. N.C. Talukdar, Director of IITGuwahati, Guwahati, former Director, Professor D.N. Raghunathan, Dean of Faculty Affairs, Dean of Student Affairs, other deans, Dean of Academic Affairs, Associate Dean of Academic Affairs, all the faculty members, students, all invited guests, ladies and gentlemen. At the outset, I wish Happy Teachers' Day to each one involved in teaching activities at IITGuwahati. And also, I would like to mention, the ethos and philosophy of this day and celebration of Teachers' Day. And probably it will not be incongruous if I pay my tribute to former President of India, Dr. Radhakrishnan, and mention, a few of his activities and the way Teachers' Day has been identified in India. As Professor Mohanta said, that Teachers' Day is celebrated almost in all the countries, but every country has its own way to identify the date. In India, 5th September is celebrated as Teachers' Day, as a mark of tribute to the contributions made by teachers at all levels to the society. 5th September is the birth anniversary of Dr. Raghunathan, who was a staunch believer of education. He championed educational reform, and also we know he was a very well-known diplomat. He was a good scholar, and he became President of India, and he was a celebrated teacher across various universities in India. In April 1909, Dr. Radhakrishnan was appointed a professor at the Department of Philosophy of Madras Presidency College. Thereafter, in 1918, he was selected as Professor of Philosophy by University of Mysore, where he taught at its Maharaja College. By that time, already he had written quite a few articles with great readership in reputed journals like the Quest, Journal of Philosophy, and International Journal of Ethics. And his first book was also released by this time when he was in University of Mysore. This book, title of this book is The Philosophy of Raghunathan Tagore. He believed Tagore's philosophy to be genuine manifestation of the spirit of India. His second book, The Reign of Religion in Contemporary Philosophy, was published short after. This was published in 1920. The first book on Tagore was published in 1918. In 1921, he was appointed as a professor in philosophy to occupy King George V chair for mental and moral science at the University of Calcutta. He represented University of Calcutta at the Congress of Universities of British Empire in 1926, where people gave a standing ovation to his inaugural talk. Then he delivered a very important lecture at the International Congress of Philosophy at Harvard University. This was September 1926. Another important academic event during this period was the invited lecture, which is known as Heward Lecture on the Ideals of Life. This was delivered at Harris Manchester College, Oxford, in 1929. And this lecture was so popular that finally, after a few years, on public demand, it was converted into a book entitled An Idealist View of Life. Dr. Radhakrishnan was a Vice Chancellor of Andhra University. He moved from Calcutta University to Andhra University in 1931, and he was there for 5 years. In 1936, Radhakrishnan named Spalding Professor of Eastern Religions and Ethics at the University of Oxford, and was elected a Fellow of the All Souls College. He moved to Oxford. The same year, again, not same year, just after 1 year, he was by Oxford University. He was nominated for Nobel Prize in Literature. In 1939, he came back from Oxford. Pandit Madan Mohan Malviya invited him to succeed him as the Vice Chancellor of Benares Hindu University. He took it up and served Benares Hindu University as the Vice Chancellor till 1948. Country was independent, and as you know, his role in politics got little more enhanced, and he was the second president of India. When some of his students and friends approached him and requested him to allow them to celebrate his birthday, he said, instead of celebrating my birthday separately, it would be my proud privilege if 5th September is observed as Teachers' Day. Teachers' Day in India was not there before. He emphasized that his birth anniversary should be celebrated as Teachers' Day by paying homage to the great teachers of India, right from the Indian sages to the contemporary philosophers of India, and now of course it is Bangladesh or of the neighboring country. Since the year 1967, 5th September is celebrated as Teachers' Day in India and Bangladesh. On behalf of the Institute and on my personal behalf, it is a joyous occasion to remember contributions of this great philosopher, Dr. Sarvapalli Radhakrishnan, and also to elevate our pride of becoming teacher, at the same time reminding the teaching community about the grave duties and responsibility of the teaching community. So we are very fortunate that on this occasion, one of the champions of science from our neighboring institute, who has been serving science and teaching hand in hand for many years, Dr. N.C. Talukdar, to enlighten us through his talk and deliver Teachers' Day lecture. Thank you very much.
Thank you, Professor Gautam Vishwas, for your good wishes to all of us and also emphasizing the relevance of celebrating Teachers' Day. As Professor Vishwas has already set the context, let me take the privilege of introducing Dr. N.C. Talukdar, who is today's guest speaker. Dr. Talukdar is the Director of Institute of Advanced Study in Science and Technology, and he is also holding the additional charge of Director of Institute of Bioresources and Sustainable Development in Far. Dr. Talukdar, after graduating in 1981 from Assam Agriculture University, went to do his MSc in Soil Chemistry from Punjab Agriculture University, Ludhiana. After his MSc, he joined the Assam Agriculture University as a scientist, and then in 1993, he went to the University of Saskatchewan, Canada, to do his PhD. Dr. Talukdar has been associated with University of Warwick, UK, and Hebrew University of Jerusalem as visiting scholar. During his career as a teacher, he has guided many PhD and MSc students. He has also been involved in institutional building in Assam Agriculture University and also in Bioresources and Sustainable Development Institute in Imphal. As researcher, his research interest lies in biodiversity and ecosystem restoration research and traditional knowledge-based drug delivery. With this, let me now invite Dr. N.C. Talukdar to please deliver the Teachers' Day lecture.
Good evening, respected Professor Raghunathan, Professor D.N. Raghunathan, former Director of IITGuwahati, Professor Monta, and other respected faculties and students of IITGuwahati. It's a great honor to be here on a very auspicious day. And for being a teacher, I feel it's a great honor. But at the same time, I also do not feel very adequate to speak to such a learned gathering. In fact, I do not have much experience of speaking in public without slides and beyond research. Actually, I had a confusion, what do I speak? Maybe my sustainability research, natural product chemistry research, I share with people, and then, or what I do. I really have confusion as to, I have to very honestly admit. Then finally I settled that maybe some random thoughts and the experience that I would like to share today as a teacher and as a student. And I believe every teacher is also a student on daily basis. And particularly when we consider this teaching as an access that is called education. We learn from students and students learn from teachers. But before I share my thoughts, let me express my heartfelt greetings to you all teachers and the students on this occasion, and also to pay homage to Dr. Sarvapalli Radhakrishnan, a great scholar, philosopher, teacher that India produced. I joined as a teacher after completing my PhD, and it was really tough to be like a teacher. I just want to tell you about 4 or 5 days ago, one Dr. Karmanik, who was working in ISST as an inspired faculty, he visited to settle some of his scholarship issues, utilization certificate. He was inspired faculty. After 1 year of work, he got a position as assistant professor in Calcutta University. And when he visited me, I had a very senior professor there by me at that time, and I asked him, how do you feel your teaching experience, how it is going? Then he said, the teaching is quite different. It's not like research. And for the first time, last about 1.5 months, I've been going to class. And every class I go, I thought of fear. Then this very experienced professor who was sitting in my room at some discussion, he said, let's see, I, with 30 years of experience of teaching, gets trepidation every time I enter a new class. The fear is always there. And this fellow, Dr. Karmanik, he felt like it made him feel, this statement made him feel that the fear is very natural. Like something happened, I think this happens to many of you who have just, if you recall your initial days of teaching, it happened to me. Someday you come back from the class very jolly, happy, because you see the aura of the students. They they have understood what you've said. That is expressed by the aura they show. And someday when you come back, come out of the room, you don't feel very happy, and you think why it happened. So you realize that actually things were not like the students didn't receive me. One particular instance I remember very clearly. I was explaining to them about nutrient cycling and sustainability in nature of the plant production. I was telling them that the leaf that falls, it gets decomposed and it releases the carbon dioxide water again for trapping the energy from sunshine. I don't think they understood. They're second year students. And I didn't feel good. The next day, when I entered the class, there was a big tree near the class, so I saw a few leaves falling. One was very intact, old leaf, no deformation, no decomposition. Another was the leaf with the leaves exposed, the veins exposed, there is no in-between part, got decomposed. And another leaf, only one petal. I brought to the class and told them that this is what decomposition means. All this material will finally, most of the biomass, most of this material that accumulated last 4-5 months during photosynthesis will again be released for renewing life. Otherwise, this creation will not be sustainable. Then suddenly one fellow, he's from rural area, he stood up and he said, sir, he spoke in Assamese, he come from rural area. He said, sir, during December, January, when we go to forest near my house, when I walk, hear a cracking sound of the fallen leaves. But I don't see those during the month of May and June or July. So is it because of the decomposition? I felt so happy. And I learned something stimulated in him. He stood ask, and this, what he said in my next year lecture, this is what I used to say, that students see raise this question, this understanding. So many a time, this, as I said, exchange between teacher and students in the process of education, it everlasting things, it continues, it goes on. We have occasion, where we get opportunity to learn. There are one occasion, I think this is important for all of us. Last year, in Association of Microbiology of India, they had a annual conference held in JNU. And in the inaugural function, Professor Robert Stout from Department of Bioscience and Biophysics of University of California was requested to deliver a lecture on this inaugural function. And particularly he was saying that kindly advise these young people, there are about 1,000 research fellows, research students, scholars from all over the country. Then Professor Stout said that I'll speak maybe 5-6 minutes, but I do not have the habit of advising, but rather I will share with them by saying what I would do if I had an opportunity to become again a research scholar going back on time. He said that if I get a chance to do PhD again, while remaining engaged in my specific focused research area, I will devote considerable amount of time to keep abreast what is happening in science today and the responsibility of the scientists and science in building society and humanity. Second thing he said, that if I get the opportunity now, I'll interact with my mentors, seniors, and fellow students more intensely than I used to do in the past. The third thing he said, very important, that I will share all the resources of the laboratory with maximum number of researchers, because these are scarce resources and funded by public. So that was a lecture that perhaps helped not only the students. At that moment I felt like a student, like there were some very important message for researcher. So I thought what a true teacher is. I think as a teacher, we have now added responsibility. Besides classroom teaching or research, each one of us is going to be given additional responsibility, because teachers are the role model and society invests a lot of trust on us. This is particularly important if you see for a common future of humanity. As I said in the beginning, sustainability is extremely important. We all know what has been happening to this world, to our common future. And teachers, to make public aware about it, to spread education, has a very important role. I again draw an example that happened about a year ago. I had a visiting research scientist from Indian Agricultural Research Institute. After his retirement, he came to ISST and stayed in the same hostel and shared the dining room with the students. And one day he expressed to me that in your hostel, the huge wastage of food. Students leave a lot of food in their plates. He was not very happy about it. And next day I find in his Facebook account, he writes a few very important statements saying that in ISST guest house there is huge amount of food wastage. In the plates they leave a lot of food. And millions of kids, youths of the third world country go to bed hungry because of lack of food. The result was, within a week time, there was no leftover food in their plates. That 60, 70 students. So this is what teachers can do magic. That simple statement. So this is what I was saying, that this is a simple instance, but there can, there are a lot of many more things remain to be done. Coming to the sustainability or sustainable development issues, it's a single most challenging issue that humanity is facing today. And to tackle this, we need the collaboration of the largest possible group of partners. And I believe that teachers, with their experience of teaching and spreading education and awareness, can play a central role in this venture. As a teacher, as a scientist, we are all fascinated, and our fascination or knowledge on a larger scale, the part of this universe, when it will die, when it will be reborn, this fascination needs to be extended to simple question of life. Where an individual life comes from and where it goes. Awareness to these simple facts of life is very, very important, and also our duty to the complex web of life on this universe is extremely important. To this small awareness building, and the teachers taking a very important role, we can do a lot. On this auspicious occasion, I pray that this awareness is built in each one of us and also take a meaningful role in spreading this. With these words, I come to an end. Thank you very much for inviting me and also giving attention. Thank you very much.
Thank you, sir, for sharing your wonderful experience with us. Your achievements and your contribution to the society inspires us and also tells us that we have a long way to go. May I now please request Professor Gautam Viswas and Professor D.N. Buraghai to come to the dais to felicitate Dr. N.C. Talukar. And Professor Buraghai with a shawl. Thank you, sir. We will now have a violin recital by Devananda Pathak.
Namaskar. Very good evening to all of you. First of all, I wish very happy Teachers' Day. Respected Director Sir, IITGuwahati, Deans of IITGuwahati, faculty members, staff members, students, and ladies and gentlemen. I am very fortunate to be a part of this program, and I shall be presenting two musical pieces. First is Raghunathan, and second piece is, it's a glimpses of folk tunes of few states of India. As in IIT, many members are from different states, so I have chosen this piece. If I make any mistake, kindly excuse me. Hope you will enjoy the musical pieces. Thank you. Rajasthan, Gujarat, Chhattisgarh, Odisha, and then finally I will come back to Assam.
other campus residents, Dr. N.C. Talukdar, Director, Institute of Advanced Studies in Science and Technology, Professor D.N. Raghunathan sir, Founder Director of IITGuwahati, Professor Gautam Biswas, Director IITGuwahati, and today's speaker, Reverend Professor M.S. Raghunathan. A good evening to all of you. As I stand here to introduce one of the legendary figures of Indian mathematics, I personally feel blessed. However, I must candidly admit that it would have been probably much easier for me to talk for 2 hours in my specialization rather than introducing an academician and researcher as great as Professor Raghunathan, who is not only a great mathematician but also a great social worker in mathematics. Having completed his school and college education in Chennai and Bangalore, Professor Raghunathan's real journey in mathematics started in 1960 when he started working under Professor M.S. Narasimhan, another great Indian mathematician, at Tata Institute of Fundamental Research, that is TIFR, Mumbai. Just to mention, Professor Raghunathan was one of only 2 selected from around 250 candidates who had applied for PhD positions. Having awarded PhD by the University of Bombay in 1966, Professor Raghunathan spent a year at Institute of Advanced Studies, Princeton University, USA. Since then, TIFR has been his workplace till recently. He has served TIFR in positions such as Professor of Eminence, Homi J. Bhabha, Chair Professor. Professor Raghunathan holds the distinction of being invited to give a talk at International Congress of Mathematicians, which is called ICM, a quadrennial and the biggest congregation of mathematicians world over, held at Nice, France, when he was only 29 in 1970. It is worth mentioning that Professor Raghunathan was the main person behind India winning the bid for 2010 ICM, which was very successfully conducted at Hyderabad, with him serving as the chairman of both Executive Organizing Committee and the Local Organizing Committee. Discrete subgroups of Lie groups have been the central objects of research of Professor Raghunathan. The Lie groups, known after Sophus Lie, who introduced them in 1873, have had tremendous impact in various areas of mathematics and physics. One of Professor Raghunathan's conjectures made in mid-1970s, known after him as the Raghunathan conjecture, has been very influential in the study of dynamics of a class of flows and their applications in various areas. Professor Raghunathan's book titled Discrete Subgroups of Lie Groups, published by Springer Verlag in 1972, is now considered a classic in this area. In a unique book titled A Panorama of Pure Mathematics, French mathematician Jean Diodor in 1977 recounted important results from various areas of pure mathematics. Professor Raghunathan was one of the Indian names in the book for having made substantial contributions, though he was still in his mid-30s when this book was published. Professor Raghunathan's role in establishing and continuously guiding National Board for Higher Mathematics, in short NBHM, since its inception is highly praiseworthy. A founding member of NBHM, he has served as its chairman for a long period and is still connected to it. Rather, he is considered as the driving force. Contribution of NBHM to the growth of mathematics education and research in the country is unparalleled. For the record, IITGuwahati has been housing a regional NBHM library since 1998 with a sizable annual grant from NBHM. At present, Professor Raghunathan holds the post of Distinguished Professor in the Department of Mathematics, IIT Bombay, and simultaneously he is the Director of National Center for Mathematics, NCM. Through NBHM and NCM, he has been unerringly providing yeoman service to the mathematics community in the country at large. In that respect, I said he is a social worker in mathematics. It is quite natural that Professor Raghunathan has added many figures to his cap with regard to winning coveted awards and fellowships. Shanti Swarup Bhatnagar Award in 1977, Third World Academy of Sciences Prize in 1991, Srinivasa Ramanujan Medal in 1991, S.N. Bose Professorship during 1993 and 96, Padma Shri in 2001, Padma Bhushan in 2012. But there are 2 more achievements that I am sure Professor Raghunathan relishes the most. Number 1, on 14 July 2000, Professor Raghunathan affixed his signature to the Register of the Royal Society, London, which also bears the signatures of Sir Isaac Newton and many other eminent names in science. In other words, he was elected for what we know as FRS, Fellow of Royal Society. He is the fourth Indian mathematician to have been elected FRS, the first being Srinivasa Raghunathan in 1980. Second one, on November 18, 1984, an eminent physicist and Nobel laureate mentioned in the Times of India, in quotes, on the faculty of TIFR now, just to mention one name, Raghunathan, he is considered by everyone outside as one of the best mathematical intellects. This comment came from none other than Professor S. Chandrasekhar, Nobel laureate in 1983, when he was making a point about what India has been able to achieve in research, and it is apt that Professor Raghunathan's name came to his mind in that respect. I am sure I am not being able to highlight all his achievements since there are too many, and also because we cannot wait anymore to listen to these great mathematicians. Let me put a full stop here and let all of us get engrossed in Professor Raghunathan's lecture. Thank you.
My talk is entitled Mathematics, Art that would rather be Science. There is not going to be much mathematics in this. There will be little bit, but nothing taxing, nothing which demands any great attention. Mathematics has been called the Queen of Sciences by none other than Carl Friedrich Gauss, one of the greatest mathematicians of all, arguably the greatest mathematician of all time. He also said, in addition, that number theory is the Queen of Sciences. I'll say more about it later, but the appellation Queen to mathematics is, I think, particularly appropriate for various reasons. Firstly, like royalty, mathematics stands a little apart from other natural sciences. Look at the title of Newton's great work, Principia Mathematica, Mathematical Principles of Natural Philosophy. So it stands apart from natural philosophy, as it gives principles which enables natural philosophy to develop. So, in that sense, it does display one of the qualities of a queen, namely an aloofness we attribute to royalty. And again, it's not called the king of mathematics, the king of sciences, what we call queen. The queen is not as important as the king ever, at least in history. Certain number of queens been important, except maybe Elizabeth of England or Catherine the Great of Russia. Queens have always been somewhat, what should I say, third page personalities. In the modern newspaper language, they belong to page 3. Well, and their preoccupations are usually not very serious. And as is illustrated by this nursery rhyme, the queen was in the parlor eating bread and honey, whereas the king was in the counting house counting out his money. Obviously, he was doing more important things, whereas the queen was being somewhat self-indulgent. It's another quality of the queen. At least that's the general perception. And there is an element of indulgence about it, and I think that's also true of mathematics. Mathematics is kind of self-indulgent. We'll come to that. Queens are supposed to be impulsive. They are supposed to take actions without thinking too much, and somewhat whimsical. And here is the queen who was whimsical and completely arbitrary. This is the Queen Alice in Wonderland. And however, mathematics is not as unreasonable as this whimsical queen. It's whimsical in the sense that what mathematicians will pursue, what problems they will attack, is something which they think of themselves. They don't refer to anything outside. Of course, they do work on problems which come from other sciences, but in number theory, for instance, you work on problems which suggest themselves to the mathematician's mind. No particular reason why one should work on them, but mathematicians will pursue such questions. So, queens are whimsical, and so is mathematics. Now, the most important quality which the popular mind associates with queen is beauty. And certainly mathematics is beautiful. It is probably not recognized widely that mathematics is beautiful, but it is, and I will say more about it presently. Why do I say it's beautiful? What are the qualities of beauty? Here is the great English poet Keats, who said, "The thing of beauty is a joy forever." if something gives you joy forever, it's a thing of beauty. And mathematics has certainly given joy for centuries to at least the mathematically inclined. Look at this book, the frontispiece of Euclid's Elements. Certainly Euclid's Elements has given joy to generations of mathematicians. It has also probably given distress to generations of other people, but certainly it has given great pleasure to mathematicians over centuries. And in that sense, it's joy forever. Well, actually the Keats quotation, it's the first line of his poem Endymion, which is something that's derived from Greek mythology, so it's a product of Greece that made him inspired in these words. But for the mathematician, this other product of Greece probably is the one which gives joy forever. Well, mathematics, I said, is beautiful. And here are other people, non-mathematicians, who give the same certificate to mathematics. For the harmony of the word is made manifest in form and number, and the heart and soul of all poetry of natural philosophy are embodied in the concept of mathematical beauty. So says a biologist, Darcy Wentworth Thompson. Biologists usually are supposed to dislike mathematics, at least biology students are supposed to. However, this man has obviously great admiration for mathematics. He's a biologist. And here is another famous statement from Bertrand Russell. He says, mathematics rightly viewed possesses not only truth, but supreme beauty. Beauty cold and austere, like that of sculpture, without appeal to our weaker nature, without the gorgeous trappings of painting or music, and capable of stern perfection, such as only the greatest art can show. So, here are opinions, and let me quote the famous Newton. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore and diverting myself in now and then, finding a smoother pebble or a prettier shell than ordinary, where the great motion of truth lay all discovered before me. So he's looking for a smoother pebble and a prettier shell. That's the search that Newton is making. Of course, Newton is as much a physicist as a scientist, as a mathematician. He's certainly also rated as a mathematician of the same class as Gauss. And he has this to say, and certainly his work, Principia, is very much a mathematical work, and that obviously is for him a matter of beautiful matter of beauty. Now, not all people perceive mathematics as beautiful. In fact, Newton is looking at all science as something beautiful. Aesthetics is certainly a driving force behind all science, though it's not often recognized as such. In mathematics, it's even more emphatic. I'll illustrate that with the other examples. But here is a famous poet who is totally against natural philosophy, and certainly that would mean he would not be favorably disposed towards mathematics. And quoting from Keats, he says, look at the last line, conquer all mysteries by rule and mind. That's what philosophy will do. Philosophy will clip an angel's wings, conquer all mysteries by rule and mind, empty the haunted air, unknown mind, and unweave a rainbow. So he thinks of Newton as the person who has destroyed something beautiful. Unwoven the rainbow is what he says. So not all people find beauty in mathematics, but luckily, while Keats has this, another poet, Alexander Pope, said, God said, let Newton be, and all was light. So there is a man who admires Newton greatly, while Keats considered Newton essentially a vandal. Okay, now, before I go on, so the point I'm trying to make is that yes, mathematics is very much a search for beauty. It is already the search for beauty is evident in the first intimations of mathematical activity. Counting is obviously the first mathematical activity that one can think of. And what does counting do? Counting is, for us now, it's almost instinctive, but what lies beneath it is something very profound. You find something common between very diverse objects, diverse collections a basket of fruits, or a bunch of grapes, or a sheaf of papers, whatever. You find there can be something common among them, namely the number of objects in that collection. There are diverse collections, but all of them have something in common. So when you contemplate very diverse collections, it's a chaos. It's not clear. But finding something common among them is for looking for some kind of order in that chaos. And looking for order in a confused state is certainly part of looking for beauty. So in that sense, already counting shows that there is beauty there in mathematics. There's a famous statement which everybody knows, which due to Descartes. He says, "I think, therefore I am," and I have this takeoff of that. I count, therefore I count. So the people who pursue mathematics can claim that they count because they pursue mathematics. As I said, abstraction is one quality that permeates all of mathematics. It consists, on the one hand, in locating common threads among diverse phenomena. On the other hand, in identifying and rejecting the irrelevant in a particular study. That's what abstraction amounts to. And already in counting, both these aspects of abstraction are manifest. Firstly, you find something common among disparate collections. So that's the first aspect. On the other hand, you completely ignore the individual nature of those collections. Whether it's a basket of fruits or a sheet of papers, you don't care what the actual material you're counting is. So what you found is something common between them, but you're ignoring their individual qualities. So both aspects of abstraction are already visible in counting. The first, this almost involuntary act involves profound abstraction, and that serves to illustrate strikingly both the complementary sides of abstraction which I described above. For example, before you could talk of let me give another example of where the individual nature of something has to be ignored completely. That is, I said in a particular, rejecting the irrelevant in a particular study. Galileo rejected friction in his first study of motion, and that's what made mechanics into a science. Before that, the whole issue was confused by the presence of by the ubiquitous presence of friction, but Galileo recognized that you have to ignore it if you want to make progress in the study of motion. So, to make the case for mathematics being beautiful, let me go back to some of the earliest work in mathematics. There is Pythagoras, who lived in the 6th century before Christ, 6th and 5th centuries before Christ, and his famous theorem tells us that the diagonal in a square of unit side has length root 2. This, of course, we take for granted. Nobody bothers about it, but Pythagoras was bothered, because what is the meaning of root 2 is what you are worried. Why is root 2 a number? For him, number meant whole numbers, then fractions, okay, and manipulating with them, it's all perfectly okay. Is root 2 a fraction in the usual sense? Is it of the form p by q, where p and q are whole numbers, with q not equal to 0? He found that that is not the case, and that bothered him greatly. Pythagoras' proof of this irrationality of root 2, which is beautiful, goes as follows. It's very simple, but very nice. Suppose root 2 is rational, and this is equal to p by q for some integers p and q, with q not equal to 0. You assume, as you may, that p and q have no common factor, because you can remove the common factors. And then p by q whole square becomes p squared by q square. That's equal to 2 is the assumption. That is, twice q square becomes p square. Thus p square is even. But if p square is even, 2q square is even. But if p square is even, p is even. So p is will form 2r, and you square it, p square therefore divisible by 4. And the left hand side, 2q square is divisible by 4, that means q square is divisible by 4, which means q is even. So both p and q have to be even, so they have a common factor, which is the contradiction. So that is the proof that there can be no number of the form p by q whose square is 2. A fairly quick and elegant proof. And so there is no rational number whose square is 2. This bothered Pythagoras. He wanted a firm foundation for everything he talked about. And he didn't have a firm, what is this root 2, this mysterious number? He didn't record the number at all. In fact, the story goes that he forbid all his students or companions from talking about square root of 2 at all. And one of them was even punished with death, is one of the stories running around. I don't know if it's true, but so strongly did he feel about this. And in fact, in some sense, this bogged down Greek progress in mathematics. Because Pythagoras' school was not allowed to talk about root 2 at all. So that certainly was a great disadvantage for further progress. Now, let me talk about another beautiful piece of mathematics, which is certainly according to Euclid, probably it's Euclid's theorem. But Euclid's elements has all these things, but one is not sure that which of those things were his own discoveries and which was simply recording of earlier discovery. This is a piece of work, this is a piece of mathematics which most mathematicians consider very beautiful. If not all, most do that. Let me recall a little bit some elementary mathematics before I can state the theorem of Euclid. A prime number is simply a number which cannot be divided by any other number, any number other than itself and 1. So, it's a number greater than 1 whose only divisors are itself and 1. The first two numbers are 3, 5, prime numbers are 3, 5, 7, 11 and so on. Euclid posed himself the following question. Is a collection of primes a finite collection? This is almost an ideal question. Why is anybody interested in knowing whether the collection of primes is finite or not? But it's natural for a mathematician to ask this question. But the outsider looks kind of strange that one should be interested in such a question at all. Euclid not only answered this question, but gave a proof which is beautiful. We will see the proof now. He answered the negative. He proved the following. The set of prime numbers is an infinite set. The collection is infinite. How did he prove this? It goes like this. We begin with the following claim. Any integer argument with 2 is either a prime or a product of primes. So, how was this claim? How was it proved? Start with pick up the element r, pick number r. Suppose if it's a prime, there's nothing to prove. If it's not a prime, it's a product of 2 numbers. Because it's divisible by something, so it becomes product of 2 numbers, p and q. And so, yeah, of course, the way I've said it, okay, I skipped this, I started out in a different way, but anyway, one proves, suppose I want to say any number is either a prime or the product of primes. I prove it by induction. Start with r equal to 2. 2 is a prime, so there's nothing to prove, so it's okay. Suppose the claim is true for all r with 2 less than r less than 10. Every one of those numbers, suppose is a prime. And now, I want to prove that n plus 1 is also either a prime or a product of primes. If n plus 1 is a prime, there's nothing to prove. If not, n plus 1 is the form a times b for a pair of integers a and b. Obviously, necessarily a and b are both less than or equal to n. By induction hypothesis, a and b have to be both less than n, because 2 is less than a, less than to b, and therefore both less than n plus 1. So they are between 2 and n. By induction hypothesis, a is either a prime or a product of primes, and the same thing is true of b. So a times b is like again a product of primes. So n plus 1 is the product of 2 or more primes. Once this is established, we'll go to the next step. Suppose the set of primes is finite. List them. P1, P2, Pn. It's a listing of all the primes. There are only n primes, so I've listed them. Now look at the number P1 times P2 times Pn plus 1. Then n is not divisible by any of the primes, Pi, 1 less than I less than n. And n cannot be a prime because my list of primes is exhausted, n is bigger than all the primes listed, n is not a prime. But on the other hand, any number I've told you is already a product of primes. So n is the product of primes, but if it's the product of primes, it has to be a product of some of these P1, P2, Pns. That's a contradiction. So n cannot be a prime. On the other hand, according to the claim, n as a prime factor, one of the pi must divide n, and that's impossible. So, even Keats may find some beauty in this because it deepens the mystery of prime numbers. Unlike Newton explaining away the rainbow colors, the mystery of prime numbers only deepens. So, maybe like this. Well, okay, now this is what the Greeks, I talked about the Greeks. Now let me talk a little bit about mathematics in India. After Pythagoras' ruling that nobody should talk about root 2, in some sense, Greek mathematics suffered a setback. And however, mathematics was going on elsewhere where they were not bogged down by Pythagoras' ruling. And among the places where great mathematics was being done was India. And India, around the, looks like it's not very clear, the dates in Indian history for practically everything is always a little hazy. But in particular case, when zero was started, when people started treating zero as a number, that's the major progress in mathematics, and one doesn't know when exactly it happened, but presumably somewhere around 5th century or 4th century AD. But the first inscription of zero in any stone inscription in India comes only in the 10th century, and you can see that number 270 written there. It is in temple in Gwalior. That's where the number 270 is found. There's an inscription of zero elsewhere outside India, in fact in Cambodia, which goes back even earlier, goes to 6th century AD. And there was an attempt by the Chinese to claim that zero was a Chinese invention. I mean, they are no different from our own chauvinists who don't want to claim all kinds of things from our ancestors. The Chinese also, as it turned out, the claim could not be sustained because the rest of the inscription was in Sanskrit. So there's no question of it being Chinese. So anyway, this is the oldest inscription, but already zero was known to, there's evidence to indicate that zero was known to Aryabhatta, who lived in the 6th century, and Brahmagupta. Once again, zero and the system of writing numbers using the numerals from 0 to 9, the place value system was of course a great Indian discovery. Again, I would say there is some beauty behind it, that one is able to write any number which one can imagine in a definite, in an easy, simple way is obviously a matter of being something, making things beautiful. And so the place value system with zero in its place is certainly an indication that there is a look for search for beauty. In fact, the place value system is extremely useful, obviously, and in some sense it's probably the most important discovery in all science. Without that, I don't think science would have progressed anywhere. So it was an important discovery. However, so one might think this is something which is result, the invention was probably the result of necessity. There's an old adage which says necessity is the mother of invention. But this place value system is really useful. It's really necessary only if you are dealing with very large numbers. And in periods like the 4th century AD or something, I don't think people were handling large numbers. Certainly, they didn't need to handle large numbers, or if you like, there were people who needed to use large numbers even earlier. The Persians and the Greeks had huge armies, and handling them probably would have required some kind of numbers which are easy to deal with, representing numbers in a way which is easy to deal with, but they didn't discover zero or the place value system. The Indians who discovered. On the other hand, the Indians are always upset with large numbers. Jain monks who were interested in mathematics had names for 10 to the power of 18 and things of that kind. Right up to 10 to the power of 18, they had distinct names, all powers of 10. And so it's more because they were obsessed with large numbers in the abstract, and they eventually wanted to be able to write down any large number you can think of in a concise way, that they probably invented this. So it's a search for beauty rather than a need to meet practical considerations. Well, Indians also knew how to solve quadratic equations. Everybody knows in school you already learned that the quadratic equation ax squared plus bx plus c has this solution. This bit of algebra was already known to Indian mathematician Raghunathan. Algebra and manipulation of unknown quantities has its origin in Babylon and Greece and independently in India. It advanced considerably in the hands of Brahmagupta. Persian and Arabic mathematicians who seem to have had some awareness of earlier work in India were responsible for further great progress in algebra in the next place. Once again, using manipulating with unknowns may have to some extent originated from practical considerations, but the way it was developed clearly indicates it became an end in itself to manipulate with them. So the subsequent, even if the foundations of algebra are based on practical considerations, subsequent development is very much an internal dynamic. It's not something which depends on outside stimulus. The word algebra itself comes from the Arabic aljabar, I'm not sure I'm pronouncing it right, meaning restoration. And taken from the title, it's taken from the title. I won't try to read that title. By book of Al-Khwarizmi, a leading mathematician of his times. That is in the, as you can see, he lived in the 8th, 9th centuries. That's a picture of Al-Khwarizmi. It's a stamp produced by Soviet Russia to celebrate this 1200th centenary. And that is the Passaman of a page from the book. And here is another famous Middle East mathematician, Persian mathematician, Omar Khayyam, who is not known so much for his mathematics. He is known as a poet. But he was one of the leading mathematicians of his times in the world, Omar Khayyam. And probably shows evidence that the search for beauty, which is certainly very much part of poetry, is a motivation also for mathematics because of this man today. Now, I come to the modern period, so to speak. This is the first great mathematician of the modern period, so to speak, that is the post-Renaissance Europe. Then there's Descartes, and that is his famous quote, I think, therefore I am. Descartes, what was his, I want to say the following. See, the science in general, the motivation is to explain nature around us, the world around us. We would like to understand what's happening. But mathematics doesn't attempt that. Largely, it is concerned with its own structures. In the beginning, of course, it may be inspired by some science. I mean, counting already probably arose out of practical considerations. I mean, you have to say, so many goats is worth so many chickens or something like that. You have to trade, you have to make some relationship between numbers and things like that. So counting probably started with that aim. But soon enough, the contemplating numbers for their own sake became mathematical obsession. Like Euclid, thinking about prime numbers. Prime numbers are not of very practical implications. There are real practical applications, certainly not in the days of Euclid. But nevertheless, he was obsessed with such questions. So, even if the original source of some mathematics may be in the real world, subsequently takes on a development on its own. And that's very much like art. Not like natural sciences. Natural sciences, people don't once a question about one particular phenomenon is answered, they move on to another phenomenon, they understand that, or maybe improve on our understanding of the earlier phenomenon by devising new models and so on. But not in mathematics. Mathematics, the questions asked are often something to do with mathematical concepts themselves, rather than anything from external. Of course, mathematics also attempts to answer questions coming from other areas. So very often there is inspiration drawn from practical questions, but there is also the inspiration which comes from within, from consideration of internal structures in mathematics. And more often, it's the internal structures that seem to make a difference rather than external questions. The way if you see the development of mathematics over centuries, you will see the internal dynamic is more important than external influences in its development. And here is the first example. René Descartes developed what we call analytic geometry, the consideration of looking at points in the plane as simply a pair of numbers. That's how geometry was converted into algebra essentially by Descartes. And he did that essentially for that reason. He introduced coordinates, and writing every point in the plane as a pair of numbers was something which he invented so that you can make progress in geometry. He certainly didn't have this guy in mind who was contemplating his profit by looking at his graph. Anyway, that's a very practical application. Of course, graphs have practical applications everywhere, and they go back to Descartes, but that is not Descartes' motivation. Descartes' motivation was essentially to renovate geometry. He wanted to expand the horizons of geometry beyond what the Greeks would consider. Greeks were looking at triangles and circles and so on, and so within their way they handled geometry, they could not go beyond that. They did, of course, work with conics. Apollonius did a lot of work on conics, and again, conics for them were simply sections of the cone. The word conic comes from that. Sections of the cone. You take a circular cone and take sections of that, and that's what they were working with. And they are not really any use in practical terms. The conics came into their own much later as useful objects, only when Newton discovered his laws of motion and Kepler found that conics go around in ellipses. Till that time, conics had no real relevance to practical life, to nature. However, Descartes still developed analytic geometry simply because he wanted to expand the horizons of geometry. With Descartes, you could consider lots of other objects, analytic objects. The ellipses and hyperbolas could be treated much more systematically and much more effectively than the older methods. And of course, there is no any kind of equation gives rise to a geometric object figure. You write some polynomial equation in two variables x, y, and you get a figure in the plane. Pxy equals 0 to give you a figure in the plane, and you can study it using purely algebraic methods. And that was, in some sense, that was the first time that algebra and geometry were fused together. Till that time, the techniques of algebra essentially meant number theory before the advent of more modern techniques. So algebra meant number theory. Number theory was the study of discrete objects, and geometry was the study of continuous objects. And so the two things developed parallelly. The Greeks had to separate the two completely. But with Descartes, the two could be married. You could use geometry to study algebraic problems, and algebra to study geometry problems. Well, and here is one more example where the motivation for development of mathematics came from within. A triple ABC of positivity is a Pythagorean triple. If a square plus b square equals c square, c is the hypotenuse, a and b are the sides of a right-handed triangle. You want all three sides to be integral multiples of a fixed unit. So can you find a Pythagorean triple is such a thing? And of course, Pythagorean triples integral Pythagorean triples may come in handy when we make building constructions and so on. And already the Babylonians knew of many Pythagorean triples. It turns out, everybody knows that 2, 3, 5 is a Pythagorean triple, 5, 12, 13 is another Pythagorean triple, and so on. But you can write down all Pythagorean triples, and here is the result. It says that Take any pair of integers p and q and look at p square minus q square whole square, 2pq and p square plus q square whole square, and your high school algebra will tell you that it's a categorical. Okay. Now, so categorical triples abound. You can, in fact, it turns out that every categorical triple is essentially like this. Maybe you have to divide by 2 sometimes, but otherwise, every categorical triple is like this. Now, here is one of the greatest mathematicians of all time, Pierre de Fermat. He was an amateur, he was not a professional mathematician, he was not a teacher, he was a judge in a provincial town in Toulouse in France. And his hobby was mathematics, it was a passionate hobby. And he had a book on arithmetic by Diophantus. Diophantus is a Greek mathematician who lived in the 3rd century AD. And the book by Diophantus was prized possession of Fermat. Fermat had the habit of writing in the margins of the book his own thoughts and his own remarks about the chapter he was studying, what content of the book. And this was one of the marginal notes which Fermat made. When studying Diophantus, the book, the chapter on Pythagorean triples. And he says in the margin, on the contrary, it is impossible to separate a cube into the sum of 2 cubes, a 4th power into 2 4th powers, or generally any power above the 2nd power into powers of the same degree. I have discovered a truly marvelous demonstration of this general theorem, which this margin is too narrow to contain. This is Fermat's note. Obviously, he thinks it's a very interesting question. And so do mathematicians in general. And for 3 centuries after Fermat, many mathematicians were engaged in trying to prove this statement, because Fermat had not stated the proof, he had only stated this, made the statement in the margin. And actually, he was a very secretive person, he didn't let anybody else know about it. In his book, he had made this marginal note, but after his death, his son published a book, published the Diophantus work with all the marginal comments of Fermat in it. And that's how the mathematical community came to know this problem. And it's not the only problem, Fermat had many other problems in that. And within about 50 years after Fermat's death, most of those problems were solved by mathematics, except this one. This statement, people were intrigued, found it beautiful, kept on at it, and it was solved only in 1994 by a British mathematician, Andrew Wiles, working in Princeton. It took all that long for this question. But this question, why are mathematics obsessed with it? The only reason is that they find it beautiful. I don't know if we are outside people who are not mathematicians will find any beauty in it, but mathematicians did find beauty in it and pursued it with great concentration. Many great mathematicians wanted to pursue it. They did pursue it, and what happened was, the result was that a lot of interesting mathematics developed, even though many of them were unable to. Till Wiles, nobody was able to prove the theorem. Nobody was able to do the proof. But in the process, they developed a lot of interesting mathematics. Much of that had no outside value, it's only as mathematics that it was developed. And it was beautiful stuff. And yeah, as I said, it was resolved only in the. Now, these are developments which are entirely motivated by internal considerations, mathematical structures, like. Of course, mathematics also has brought from outside, from physics in particular, and we know that calculus was essentially developed by Newton to study motion. But 3 centuries before Newton, calculus had been discovered in India. Not for describing motion, so there are different reasons, say what it is presently. There is a school in Kerala, headed by a mathematician by name Madhava, who had the essentials of calculus, limit processes, and the idea of a derivative, and some basic notion about integration were all available, were all developed by a group of mathematicians in Kerala, headed by a man by name Madhava. Madhava lived in the 14th century, and he and his successors went on performing at a superior level in mathematics till the 16th century. So 2 centuries they were active. After that, the school died out. And here is one of the last people of that school, Jyeshtadeva, published a volume called Gadita Yukti Bhasha in Malayalam. It's very unusual that you find a text in one of the local Indian languages rather than Sanskrit, a scientific text. But this was in Malayalam. And it was translated, people are not aware, actually already in the 19th century, a Britisher by name Bish had found this book and had remarked that something like calculus had been discovered, but it was not taken notice of by the public in general, even the mathematical community. It's only in the 60s that it became, in the 1960s that it became common knowledge that these people had developed calculus. There's a man by the name K.V. Sharma who translated the Yukti Bhasha into English but did not publish it. This book was published about 10 years ago, maybe, or maybe a little more than that, or little less. Published by 3 authors who used K.V. Sharma's notes to make a more elaborate translation. So calculus has been discovered, but for example, among other things, calculus leads you to power series expansion for trigonometry, like sin x, cos x, and so on. This is all done by these people. And their motivation seems to be more computational rather than anything to do with motion. They wanted to calculate sines of angles to a great degree of interest. And it is in that context they seem to have developed the power series for sin x, cos x, and so on. So, that seems to be the motivation. Okay, now, that is, once again, there was some practical consideration even for the Madhava school, but going back, I'll give you another example of motivation which was internal, did not come from external stimulus. Here are 2 mathematicians, Hendrik Abel, who was born in 1802 and died young, 27 years, and Everest Galois, even younger and died younger, he was only 21 when he died. These are both mathematicians are recognized as having contributed tremendously to mathematics. 2 of the all-time great in mathematics. What did they do? Abel, I told you that the quadratic equation had been solved long ago. Already in the 5th century, 6th century, Indian mathematicians knew how to solve the quadratic equation. And then, of course, the attention moved to cubic. Once again, cubics, quadratics do turn up in various contexts, in applications, but the cubic already is rare that you find the cubic has any application, cubic equation. But nevertheless, the mathematicians was curious, and they did solve the cubic equation, like what they did with the quadratic equation. You have to use the coefficients, make combinations from them, add, subtract, divide, and so on, and then also take cube roots. Square roots are enough for the quadratic equation. Obviously, cube roots will be necessary, and so you add cube roots, then they solve it. Then they move to biquadratic. That is also done. 4th degree equation was also certain. And then 5th degree, all this was done by the 12th century. Now, from then on, attention went to the 5th degree equation. 5th degree equation defined all kinds of effects. Went on for several years, and then came this man Abel, who actually showed that it's not possible to do it for the 5th degree equation. In other words, you take the 5th degree equation, take all the coefficients, and manipulate with them whatever you like. You add, subtract, divide, and so on. Also, from the numbers you get as a result, you again take square roots, cube roots, everything, all possible things, and keep on doing this. You get a whole lot of numbers. He showed that there is a 5th degree equation whose solutions will not be in this collection of numbers, whatever you do. It's called solving by radicals. So Abel proved that you cannot do it for the 5th degree equation in general. And this came as a total surprise. And, well, Abel was a Norwegian, as I said, and Norway in those days was not a particularly rich country, and he himself came from a relatively poor family. And to add greater difficulties, his father died really when he was 17, leaving behind, he was the eldest of 11 siblings. So he had to support the family and so on. So he had a very difficult time. Though his teachers recognized that he was extraordinarily good, clever mind, and they tried to help, but they themselves were not in a position to be able to help him. Eventually, after some years, they found the money for him to travel abroad, to go to Paris and Göttingen, which were the great centers of mathematics in those days. So Abel traveled to these places, but unfortunately, nothing came of that. In fact, the greatest mathematician of all time, Gauss, was in Göttingen, and one of the high priests of mathematics in Europe, Cauchy, was the leading light in Paris, but neither of them paid any attention to Abel. Abel sent his work on fifth degree equation to these two people, but they did not pay any attention to it. So he returned to Norway after a year of travel, a very disappointed man, and contracted tuberculosis and died the next year. The day after he died, there was a telegram from Berlin offering him a professorship in Berlin. So it's a very tragic story of Abel. Recognition didn't come to him before he died. Compared to that, Ramanujan's story is a much pleasanter story. After all, he was recognized as a great mathematician during his lifetime, even though he died very young. And the other man, Tavares Galba, as you can see, died at an even younger age. He went much further than Abel. Abel only said the fifth degree equation cannot be solved. Galba wanted a reason why the fifth degree equation could not be solved. In fact, he wanted to tackle any general equation of any degree whatever, 5 to any degree n. He wanted a criterion to decide when an equation of degree n can be solved by radicals, when the root of that equation lies in the numbers created by this process I mentioned. And he succeeded in finding a very beautiful theory, which is called Galba theory, which is even today considered fairly advanced mathematics. I think in IITGuwahati, it's one of the elective courses in the master's program. And it's a very advanced subject, and it's a very beautiful subject. And he found this solution. And the story is that he actually was recognized as very bright by his school teachers, but he appeared for the entrance exam with École Polytechnique, which is, if you like, some kind of IIT in France in those days, and they failed the exam not just once, twice. So he couldn't get admission to École Polytechnique. And the second time he appeared for an interview, and apparently was very annoyed that the interviewers could not understand what he was saying, threw some chalk set and walked out. Actually, he was selected. I think École Polytechnique is still trying to live down that episode. But anyway, such mavericks are probably difficult to handle anytime, anywhere. He then made a living by giving tuitions to mathematics students in schools. That's how he lived. And the day before he died, he hastily wrote up a manuscript in which he described his theory, which is now known as Galba theory. And he died in fighting a duel against somebody over a woman. So goes the story. So that is Galba. So both these guys were motivated by purely internal mathematical considerations. As I said, equations beyond the quadratic or the cubic have no earthly use anywhere else. I mean, the science which uses mathematics most is physics, and even the physicists don't have much use for anything like a fourth degree equation, to say nothing of even higher degree equation. But the mathematician is curious. He wants to know whether he can solve it by radicals or not. And he goes on, Galba found a beautiful theory. And modern number theory is very much dependent on what Galba did. And like even Andrew White's work, which called different math class theorem, has not to do with Galba theory. So Galba theory couldn't have been done. And here are two 19th century mathematicians, both famous. On the left is Fourier. Fourier is a name familiar to physicists and many other scientists. On the right is Jacobi, who is probably not that well known outside mathematics, but the mathematicians certainly consider Jacobi as the greater mathematician. and there was some kind of exchange between them. Fourier admonished the younger man, Jacobi, for being obsessed with pure mathematics and not paying enough attention to applied mathematics. That is wasting his time is what Fourier said. And here is Jacobi's response. A scientist of Fourier's caliber should know that the true end of science is the greater glory of the human mind, and under that title, a question about numbers is worth as much as a question about the systems of the world. That was Jacobi's response to Fourier, upholding the inspiration which comes from internal considerations of mathematics rather than what comes from outside. I think in general, great mathematicians, or maybe I should qualify by saying great pure mathematicians, set greater store by the internal stimulus rather than what comes from outside. This is illustrated by and in all this, it resembles art more than science. Art is essentially internally generated. Its inspiration is largely internal. And so is mathematics by convention. Here is another great mathematician, considered sometimes the greatest of the 20th century. And he had this notion that, in fact, he distanced mathematics even away from other sciences. In the sense he said, mathematics is a game where you have certain rules, you make certain assumptions, make certain rules of deduction, and you follow that game. You are starting with assumptions, you make other conclusions. Then those conclusions are relevant or not is immaterial. Your assumptions are considered truths, but it's only relative. I am only stating if something is true, if something else is true. There is no question of absolute truth in mathematics. The whole thing is a game, and if it happens that it models something in the real world, that's an accident, but I am not unduly bothered about such accidents. And my interest is to develop this game. I play this game and get as many facts about I can, starting with specific assumptions. These are not absolute facts. These are facts only if the first assumptions are true. That is Hilbert's principle. And in fact, he wanted to go one step further. He wanted to prove some kind of internal consistency of mathematics. That is, you won't arrive at any contradiction if you follow this rule. You make your assumptions, and then you play this game, and you won't arrive at internal contradictions. But that was that hope didn't materialize because another mathematician, Gödel, proved that you can always formulate things which can be neither proved nor disproved within the framework of pure rules. So we cannot be sure that everything is consistent. Well, mathematics, as I said, certainly much of the inspiration of mathematics is internal, derived from internal. That may be true, but nevertheless, it turns out that all this mathematics developed for internal reasons does become useful at a later point. There are many examples of that. For example, here is a statement by a Nobel Prize winning physicist, who said, who wrote an article in a mathematics journal. The title was The Unreasonable Effectiveness of Mathematics in Natural Sciences. What he was saying is that mathematicians develop various things in some context which is purely mathematical, and it turns out it is very effective in describing nature. In the natural sciences, it comes in very handy. There are numerous examples of this kind. Yalba developed this theory. In particular, what is now known as group theory came out of that. Group theory has become very important in quantum mechanics and elsewhere in crystallography and so on. But the original motivation for developing group theory came from algebra, pure algebra, and other related things. But ultimately it became very useful. Another example is relativity. Einstein's relativity could not have been developed without Riemannian geometry. Riemannian geometry was developed by Bernard Riemann purely as an aesthetic experience. I mean, he developed like what Descartes did much earlier. He wanted to expand the horizons of geometry, and he introduced Riemann geometry with that in mind. And that turned out to be absolutely important for relativity. Without Riemann geometry relatively couldn't have been developed. So there are numerous examples of mathematics which is developed internally actually becomes very important in applications. And that is what Paul Wigner meant by the title of his talk, of his essay, which said, Unreasonable Effectiveness of Mathematics in the Natural Sciences. That is Riemann for you. Riemann's motivations entirely internal. He has his collected works is a short collection of about 15 or 20 papers. Runs not more than 400 pages. But each paper has given rise to a whole new development in mathematics. Whole areas of mathematics have developed out of Riemann's papers. At one end of the spectrum is number theory. At another end of the spectrum is, I shouldn't say another end. One end, number theory is there. A lot of current mathematical physics also goes back to Riemann. And this number theory, geometry, think whatever important subject is there, you can trace it back to Riemann. And here is another quote from a biologist, the greatest biologist of all time, Charles Darwin. What is, every new body of discovery is mathematical in form, because there is no other guidance we can have. Imagine a biologist saying it, especially in the context when you find most biologists dislike mathematics. And the greatest of them says mathematics holds the key. And here is physicist Hermann Weyl. My work has always tried to unite the true with the beautiful. And when I had to choose one or the other, I usually chose the beautiful. His work is highly mathematical. In fact, he has done work which is pure mathematics, but he has also done a lot of interesting work in physics. And he developed what is known as gauge theory in order to explain gravitation. But it failed miserably to explain gravitation. But he still pursued gauge theory because it was beautiful. As it turned out, that same gauge theory has now become important in physics again because of quantum chromodynamics. I don't know what that means. That's an area in which apparently gauge theory plays an important role. Okay, going back to Keats again. We talked of truth, mathematics. Hermann Weyl spoke of truth. But as I said, for mathematics, truth is relative. But nevertheless, here is another statement from Keats. Beauty is truth, truth, beauty. That is all you know on earth and all you need to know. And certainly, by this criterion, mathematics qualifies to be beautiful. And one more physicist making a comment. Mathematical beauty cannot be defined any more than beauty in art can be defined, but which people who study mathematics have no difficulty in appreciating. So says Dirac, one of the great physicists of the 20th century. Now, in every creative endeavor, there is always a certain amount of tension between imagination on the one hand and discipline on the other. In mathematics, one recognizes the discipline in the sense everything has to be rigorously proved. Any statement which is made, you have to prove it rigorously with arguments and so on. But that is not the only disciplining factor. The more, in some sense, is even more important disciplining factor is that it has to be beautiful. You don't see, mathematicians can ask millions of questions about mathematical structures, but they end up pursuing only some. Many of the things are thrown out because they are not beautiful. Beauty is the disciplining factor in mathematics, and so it is in art. And in this sense, certainly mathematics resembles art closer than science. Nevertheless, the mathematicians are more comfortable in the company of scientists rather than artists. Artists probably take a dim view of mathematics like Keats would of science in general. Scientists have a greater appreciation of mathematics, if for nothing, because it can be useful to them. The artist doesn't seem to have any use for mathematics. So it is in the company of scientists that mathematics is more comfortable, which is the title. Art that would rather be science. I am more comfortable in the company of scientists. Well, that's all I want to say. Thank you very much.
Thank you so much, sir. I have to confess that it is beyond my vocabulary capacity to express how motivating and inspiring your talk was. What I could just say is that this talk was not only that it was full of science, but also I'm sure everybody is charmed by the expression and articulation of explaining difficult things in such a simple way. And no doubt, sir, that is why your contribution. Thank you so much. May I now please invite Professor Raghunathan, Director IITGuwahati, Professor Prasad, Dean Academic Affairs, and Professor Lian Boragahai, Founder Director of IITGuwahati, to please come and felicitate Professor Raghunathan. May I first request Professor Prasad, Dean of Academic Affairs, to please felicitate him with the bouquet and a Professor Vishwas to please felicitate Professor Raghunathan with a memento